The digital system consists of two types. One is combinational circuit and another is sequential circuit. Okay. Now a combinational circuit consists of logic gates where output are at any instant and are determined only by present combination of input without regard to previous input or previous state of output. That means the circuit which is made by the basic logic gates, and this should not have any input like a previous output. Okay, it is not related, like no feedback system is there. Okay, if we get the output previous output, that means the feedback. Okay, but in that case it is purely input dependent, not the earlier state dependent. Okay, this type of circuit is called the combinational circuit. A combinational circuit perform a specific task, information processing operation assigned logically by set of Boolean functions. Okay, now we are implementing the circuit by the Boolean functions. That circuit are called the combinational circuit. Now what is a sequential circuit? A sequential circuit contain logic gates as well as memory cells. Okay, it need logic gate and memory cells, because I told you sequential circuit is dependent on not only the input, it depend on the previous output also. Now when we told previous output, that means there is need a place where the previous output will be stored, and the storing is come out, then memory cell is introduced. Okay, so for sequential circuit we not only need the logic gates as a input, we need a memory cell also. Is it clear? Okay, their output depend on the present input and also on the state of memory element. Since the output of sequential circuit depend not only on the present input but also the past inputs, the circuit behavior must be specified by a time sequence of input and memory state. So see here, this is a combinational circuit block. Okay, there is a input, maybe n variable input. Okay, and it is a output. It depend on the input only, not the previous state. Similarly, memory cell is a cell where we can store a bit of information. Okay, it is called memory cell. Where we can store data, this is memory cell. Clear? Where we can store data, this is called memory. Like our SD card, hard disks, and those are used for storing the data. Okay, so the basic concept is where we can store the data, it is called memory cell. The hard disk and another storing device is made by the million of memory cell. The basic element of any storing device is a memory cell. Okay, where you can store at least one digit, one binary digit. Okay. Now a combinational circuit consists of input variables, logic gates and output variables. The logic gate accepts signal from input and output signal are generated accordingly to the logic input. Whatever input you give, whatever circuit you build, whatever logic you implemented, depending on that the output will be generated. Okay, it is the basic one. So this circuit is called combinational circuit. Now the binary information of given data transform to desired output data in this process. Both input and output are obviously the binary signals. It is mandatory. Every time when we do any digital circuit, we have to have it in our mind that in that case the all input are binary and we can get the output also in binary. So the input and output signal of two possible states. One is logic 1 and another is logic 0. Because we know binary is depend on the two digit. One is 1 and another is 0. And there are an n number of input variables coming from the electric source and m number of output. Okay. It depends on what type of you circuit build. And see another important term, for n number of input variable to a combinational circuit, 2n possible combination of binary input state are possible. The statement, the justification is, if we get, suppose n is equal to 2, n is equal to 2, then how many combination is possible? 4, 2 to the power n. Why? Suppose we have a two variable, one is y, another is x, and result is in q. Then what happen? What are the combination we can build with these two input? 0, 0, 0, 1, 1, 0, and 1, 1. So see, we can we need a four variable, four different state by combine two input. That is why this statement is come. For n number of input variables to a combinational circuit, 2 to the power n possible combination of binary input state are possible. Is it clear? Is it justified?
Variable and a binary input.
No,
are they one and the same?
Both are the same. Input variable in that case, okay, it should be binary. When we function work with a digital circuit, then input should be binary.
Okay. Yeah. Okay.
Okay. Now design procedure. In any combinational circuit can be designed by the following steps. What are the steps? The problem is stated. The first one. What is your problem? What is going to be? What you want to solve? You have to write this state first. Identify the input variable and output function. The input and output variable are assigned a letter symbol. The truth table is prepared that completely define the relationship between the input variables and output function. The simplified Boolean expression is obtained by any method of minimization, algebraic method or Carnot map method or tabulation method. You can use any method to simplify it. A logic diagram is related from the simplified expression using logic gate. Okay, now I give you an example. Suppose we have to build a logic like that. Suppose we have two light. Okay, we have suppose one light. Take one light. Sorry. Now we have two switch. Now we need a relation that either one switch is on, another is off, our light should glow. If both the switch is on, then our light off, and both the switch is off, then also our light is off. It is our condition. So then condition 1 is, if suppose it is a X, so we need a circuit, the logic should be like that. Suppose one input is X, another input is Y, and output is Q. Now we need, if X is equal to 0 and y is equal to 0, then output will be what? 0, because both the switch is off. 0 means off, then our light should not be glow, so output should be 0. Now if both the input are 1, then again I told you the output should be 0. The only case, if x is equal to 0, y is equal to 1, then it should be 1. If x is equal to 1, y is equal to 0, then should be 1. Because I told you, one switch is pressed and another is open, then your light will be glown. So this is the condition we make a truth table. Okay, we make a truth table. Okay, now it is a M0 numbering it. It is a M1. It is a M2 and it is a M3. Now make a Carnot map. Two variable Carnot map. Here is X and here is Y. It is a M0. It is a M1 0. This is 2. This is 3. Now see, from this truth table, it is 1, it is 1, and those are 0, so we not give. So see, we cannot make a pair. Okay, it is 0, it is 1, it is 0, it is 1. So we have to make a single round. Now Q is equal to, then what? This loop 1, suppose it is loop 1 L1, it is loop 2 L2. So it should be L1 plus L2. Now what will be the L1? Rahul told me. What will be the L1? Tell. What will be the L1? Everyone try. Siddharth try. Here the input is XY. Srinivas, look, not AB. Okay. No, yaar. Siddharth is right. Ever B, instead of ever B, it should be X bar Y. Because for this row, X is 0, that is why X bar, and for that, the Y is 1. And now for that, it should be X Y bar. Okay. Now this logic is for XOR gate. It is the truth table of XOR gate. So we have to introduce XOR gate here. So it is your circuit. If we connect a XOR gate with these two input, then we can get this logic condition that only either one switch off and one switch on, our light should on. And if both the switch is off or both the switch is on, our light should off. So this logic is implemented by this way. So it is the procedure to make a combination circuit. We have to first think our logic, then make it a truth table, then put it in a Carnot map and simplify it. It is a equation of XOR gate. Is it clear? it is also a truth table of XOR gate. Is it clear? In that way, we have to build our circuit. Whatever logic come from your brain, you can make the circuit accordingly by this process. So in digital world, nothing is impossible. Whatever you can think, you can implement in your circuit. It is a interest of digital electronics. Okay, now see. Now we go for the two basic circuit of half adder and full adder. Okay, now see, the simple addition consists of, see here, the simple addition consists of four possible elementary operation, which are, if we add 0 plus 0, it will return 0. If we add 0 plus 1, it will return 1. 1 plus 0, it will 1. 1, 1, it will 1, 0. 1, 0 means 0 is your answer, 1 is carry. Okay, 0 is your answer, 1 is carry. So the first three operations produce sum of one digit, but the fourth operation produce sum of consist of two digits. One is first digit and second one is carry. So it consists two digits. So the sum consists of two digits. The higher significant bit of this result is called carry. A combinational circuit that perform the addition of two bits as described above is called half adder. Once again, a combinational circuit that perform the addition of two bit, mind it, 2 bit, 1 and 1, 2 bit, it as described above is called half adder. When the augment and addend number contain more significant digit, like that one, the last one, we add two single digit but the answer is two digit. In that case, the carry obtained from the addition of 2 bit is added to the next higher bit pair of significant bit. Suppose like that, 1 plus 1 in decimal, it will be 2. It will be okay. But if we add 7 plus 7, then it will return 14. So if you have a single digit representation, it will show 4. But this 1 is a carry. Your circuit has tendency or capability to show 1 digit. So for this addition, it will show the correct answer, 112, because answer also in single digit. But in case of answer 2 digit, then your circuit cannot capable to show the correct answer. If we use our old circuit to add this 7 plus 7, your answer shown 4. It is incorrect, because carry is 1 which cannot be shown because it don't have the provision. For that case, we have to need the extra bit, and it is called full adder. Okay, full adder work is, suppose we have two digit of number 1, 7 and 5. Then what happen? There 2 and the 1 is in carry, which is added with the next digit. So in that case, this carry should be calculated. Neither your answer will be wrong. So it is the operation of 2 digit addition, and it is called the full adder. Okay, now in below we will see and we can understand better way. See the design of a half adder. Is it clear whatever I told? What is a half adder and what is a full adder? Half adder means it can be add only single bit. It cannot consider if your addition generate carry or not. But in case of full adder, if the carry is produced, it can be calculated. Okay, is it clear? If carry is generated, it should be calculated in full adder. But in case of half adder, it cannot be calculated if carry is generated. It is a single bit representation. It is a single bit addition. It can perform in half adder circuit. Okay, see here. As described above, a half adder has two input and two output. Let the input variables and addend as described A and B. See, 0 0, if we add 0 0, it is 0. 0 1 1, 1 0 1, 1 1, the output is 0 and carry is 1. Okay, now by this, watching this, we have to make a truth table, or we know, you already described in the next problem that it is a truth table of XOR gate. We see here, na? See, 0 1 1 0, then it is X bar Y and XY bar. See here, A bar B and AB bar, because here two input is A and B. Okay, and for that, see, this truth table is for what? Which gate? 0 0 0 0 1 0 1 0 0 and 1 1 1. It is for which gate? Tell me. Yes. So see, the relation of this output S with AB input is like that. S is equal to A bar B, AB bar. And the relation of carry with input is AND. So XC is equal to AB. It is a relation of AND gate, A dot B. Okay. Now see, it is a XOR gate circuit. So we can get the S by just only giving a XOR gate, see, and we get the carry by giving a AND gate. So we can prepare our half adder circuit. How easily? Is it clear? See, if we want to add 1 and 1, suppose here 1 1. Now tell me, for 1 1, what will be the output of XOR gate? Tell me, what will be the output of XOR gate if both the input is 1? Okay, so it is 0. And what will be the output of AND gate if both the input are 1? Because this one is fitted here, this one is fitted here. So what will be the output of 1? So see, now it is come. The output is 0 and sum is carry is 1. So by using this circuit, you can verify the all combination of addition for a single digit. Okay. See. Is it clear?
Sir,
Tell.
so there will be two outputs. In the previous classes we have seen one output. Here you are saying it will be two output.
Because of two output, we need the two gates. One is XOR gate, another is AND gate. Yes, because we have to implement the logic. Without carry, we cannot add the two digit, because when we add 1 and 1, it generates 0 as an output and 1 as a carry. So we need the carry also. That is why we implement the both logic. One is output logic, S is equal to A bar B, A B bar, and another is carry logic. Carry is A B. So that is why we use two gate to generate two different output.
But in the previous one, we have if A and D are 0, 0 on the left side in the table, truth table, we had one output, right?
One output, in that case carry will be 0. 0 means nothing.
Yeah, okay.
That is why if you put the 0, 0 here, see what happened. In 0, 0, also your S will be 0 and the AND will be 0.
Yeah. So why in first place we are considering the second output? Sir, I'm not in from electronic.
No, because see, we need a provision where for every single digit addition we can fulfill. We can find that for 1 addition we need 2 digits, 1 and 0. That is why we have to implement the carry section. If it is not if it not needed the 2 digit, then we cannot need this carry 1. But without this carry 1, we cannot do this implementation. Above 3 will be possible, but the last one is not possible. So that is why we have to make like that. Because you don't know what type of addition your circuit has to be done.
Okay.
That is why we have to give the provision.
Okay. Yeah.
Okay. Now see, design for full adders. A combinational circuit of full adders perform the operation of addition of 3-bit. The 3-bit means what? First you understand. See, 3-bit means that X, A, B. This X is a carry or other thing. Okay. See, I just told you, in case of addition of these, we need another digit that is called carry, because this carry should be added with that, then only our addition is completed, neither not. Okay, so a combinational circuit of full adder perform the operation of addition of 3 bits, the addend and the previous carry, and produce the output sum and carry. Okay, it will calculate previous carry. Okay, see, that means we add this digit and it will generate carry, then we have to calculate this carry also. We have to add this carry also. See how? Suppose the input variables is A, B and carry is X. So, and the output sum, okay, I just told you, suppose we have a half adder. Okay, now suppose it is a half adder. Now it has two provision, two input and two output. One is output, another is carry. Okay. Now we have another half adder. this half adder can add only, by 2 input we can add only 0 0, 0 1, 1 0 and maximum 1 1. So it is a 0 in decimal equivalent, it is a 1 in decimal equivalent, it is a 2 and it is a 3. Okay. Now what happen? Suppose we have to add 2 plus 2. Then what happen? Sorry, we just did a mistake. Basically this input can add single bit 0 or 1. Okay. Now suppose we have to add 0 0 and suppose 1 0. Then what we will do? See, first not take that, we take this type of example. Suppose 0 1 and 0 1. Okay. Then maybe it 1 also. 1 1 plus 0 1. Then see, those are 2-bit input. In half adder we can get only single digit input. Am I right? One is 0, another is 1. But we need two digit input. Okay. So for that case, we need another half adder. Suppose to perform this 1 and 1 addition, suppose this portion we can add with half adder 1 and this portion we add with half adder 2. So for this portion half adder 1, so this input should be 1, it should be 1. So output should be 1 1, it 0 and the carry is 1. Okay. Now for this half adder it is 1 and it is 0 because it will add this portion. So now what happened? The earlier digit produce 1 1 0 and 1 carry. Then as per our addition rule, this 1 should be add with that. Am I right? Can you understand? Okay, see. Suppose we have to add two number. One is 1 1, another is 0 1. So by half adder we can add only single digit. Okay, it is a x and it is a y. So for x there is a 2 portion. We can add these xy and this xy. See, if we add in like that way, we can do same thing like that. 1 1 0 and carry is 1 in hand. Okay. Now these 1 add with that, that is 1 1 0 and 1 is carry. Am I right? In that way this addition is performed or not?
Sir, in the first one, 1 1, how you got that 0 there?
Suppose you take forward. See here, you take this decimal addition. If it is 8, then what we will do? 8 8 16. Then 6 here
16,
and 1 is carry, and this carry should be add with this 1 1 2 na.
Yeah.
So same thing in binary also. 1 1, this 1 add 0 and 1 is carry. From where we get? From here you get. If you add 1 and 1, the result will be 0 and carry is 1.
If you add 1 1.
Acha, tell 1 1 what?
It will be 0 and
0 and 1. Okay. Carry is 1.
Okay, you are. Oh, so you are referring to this circuit, the one in the drawing.
No, actual what? 1 and 1 is in 2. Am I right?
Yeah.
In 2 in binary what? 1 0?
Or 2, okay. 1 0, okay. Okay.
So 0 is sum, 1 is carry?
Yeah.
This implement here, see 1 1, if we add 1 1, 0 is sum and 1 is carry? So,
okay.
So that is implement here. If we add 1 1, 0 is here, 1 is carry. Now how we add this carry? See here 2-bit representation, because x had 2-bit, y has 2-bit. But we know in our half adder we can add only 1-bit number. If it is x is equal to 1 and y is equal to 0 or 1, we can add by our half adder. But now x is equal to 1 1 and y is equal to 0 1. That means x has 2-bit, y has 2-bit. So we can at least need 2 half adder. Am I right or not? Because for these 2-bit we need 1 half adder to addition, and for these 2-bit we need another half adder to addition. Is it clear?
Sorry, can you repeat, sir?
See, one half adder can add only 2 single bit.
Okay.
So for adding 2-bit, how many half adder we needed?
2.
2. That is why I tell you na. So these 2-bit will be added at 1 half adder, and these 2-bit will be added in another half adder. Am I clear? Is it clear, Srinivas? Hello?
No. Yeah, no. No. I don't know. Everyone has the same issue, and I'm losing your voice suddenly.
Okay, maybe some network problem. Now, can you hear me?
Yeah, now I can hear.
Okay.
Yeah.
See, for addition that one, so we need 2 half adder. All are agreed?
Okay.
Because this is a 2-bit addition, and 1 half adder can add only single bit addition. So for 2-bit addition we need 2 half adder.
Yes.
Is it satisfied all? Okay. Now see, it is the LSB lower significant bit and it is the MSB most significant bit. So in for decimal addition, we start with lower significant bit. This side से चालू करते हैं ना? So we take a half adder and did the lower significant addition of 1 1. This 1 and this 1. Then what will be our sum and carry? জলের বোতলটা দে তো। Tell me, what will be our sum? 0 and the carry is 1. Okay. Now it is half adder 1. Now in half adder 2, the addition is done for most significant with these two digit. Am I right? 1 and 0. Am I right now? Because we have to add these two. Am I right, everyone? It is half adder 2. As per you people agree with me that these two addition need two half adder. One half adder can add this less significant bit and another half adder is add this most significant bit. Am I right? Hello? Siddharth, can you hear me? Srinivas, can you hear me now?
Now we can hear sudden.
Okay. Sometime network is
yes.
problem. Okay. Now tell me, is it satisfied that for this addition of second half adder, we need the second half adder or not? And this half adder input should be 1 and 0 or not? 1 and 0? Because it can add this lower significant bit, a most significant bit. Is it clear to all? This much is clear to all? Srinivas, it is clear to you? Okay. Now see that one. When we add, the carry is generated, carry is added to the most significant bit. Am I right? And for this operation also, 1 1 and 0 1, we need what? 1 1 0, 1 carry is generated, so this should be add with these two. Am I right? But in your another half adder, it has a provision of adding 2 bit only. Then how can you add this carry? So is it possible to complete your addition? How we add this carry? Because this half adder has only provision to add 2 bit and this 2 bit is already given x and y. Then how can we add this carry? Is it clear what I want to say? So for that purpose we need a circuit which can add as usual the most significant bit and carry also. 3 input addition. Is it clear? It is called full adder. It has a provision of 3 bit. One is for carry and another is for 2 bit. Is it clear? That is why I told that full adder has 3 input, 3 variable input. Clear? What is the difference between half adder and full adder? Srinivas and Rahul?
Sir, can you repeat?
See, in these 2 half adder, can you complete the operation? Because this half adder can add these 2 bit and these this half adder can add the most significant bit. This 1 and 0. One input is 1, another input is 0. Okay. Now how can we add the carry generated in previous adding? Because see this, see that one. In least significant bit we add 1 1. The result is generated 0. But it will produce one carry here. So in next this bit addition, how many input we needed? 3. But your half adder has a provision of 2 bit. So can you add with half adder? So you need a device which can add 3 bit. Am I right? It is called full adder. That is why I told full adder has a 3 input and 2 output. It can add 3 input. Is it clear difference between the half adder and full adder? Yeah. Now come back to the circuit. Srinivas, please off your microphone. Okay. See, I already shown that the input variables of a full adder has 3. One is A, another is B, and another is previous carry if generated. Because we need 3 input. See, one is for carry, this X is for carry, and A and B are normal. Okay, so it has a truth table like that: 0 0 0, 0 is here, 0 is carry. Now if we add 0 0 1, then 1 and 0 is carry. Now again 0 1 0, it will 1 and 0. Now if we add 0 1 1, what happens? See, 2 1 is present, so sum is 0, carry is 1. Now for that 1 0 0, it is 1. Now again 2 1 present, so for addition 0 will be here and 1 is carry. Now again it is 2 1, again same thing, 0 is sum and 1 is carry. Now see, here 3 1. So if we add 1 and 1, it will produce 0 sum, 1 in carry. Now we add again 1 with that, then what happens? Sum also 1, carry also 1. See, is it clear? This truth table is clear to all? See, if all are 0, then sum is 0, carry is 0. Now 2 digits are 0 and 1 is 1. So anything add with 0, it is 1. If you add 1 with 0, then 1 is produced, carry is 0. Now again it is same, 0 plus 1, answer is 1, and this 0 is added with that, then answer remain 1, no carry is generated. So here, now see, this is 0 1 1. Now in first case, if you add these two, 0 and 1, it will generate 1, no carry. Now again another one we have to add. Now if we add this one, then it will produce 0 and 1, because 1 1 0 and carry is 1. See here, 1 1 0 is sum and carry is 1. Is it clear, Siddharth? In that way, if we complete this, then we get this truth table. Is it clear, Siddharth? Is it clear to you? If you have any confusion, please ask. Specific which step you not understand, ask. No problem. Okay, see that is left. Now see, now we have to implement this in Kano map. It is a 3 variable input, so we make a 3 variable table. Now in which place we find 1, see, in position 2 we find 1, so in position 2 we give 1. Now in position 3 we find 1, so in position 3 we get 1, because the number is like that, 0, 1, this is 2, and this is 3, this is 4, this is 5, this is 6, and this is 7. Am I right? Now it is the place of 0, it is place of 1, it is place of 2, it is 4, and last one 7. Now match. Is it match? For place of 1 there is a 1, for place of 2 there is a 1, for place of 4 there is a 1, and then the last one, the place of 7, there is a 1. Okay, now we can make any loop? No? We have to make the single loop. So it is a L1, suppose it is a L2, it is a L3, and it is a L4. Okay, now see the Boolean expression from the Carnot map. S is equal to x bar a bar b. Okay, so it is a relation of sum. Now if you implement the carry, then carry in which place this is 1, 0, 1, 2, 3. Third place it is 1, and fifth place it is 1, sixth place it is 1, and seventh place it is 1. See, third place, 5th, 6th, 7. So we can make a loop like that way. Okay, it should be like that, not 3 variable. Okay, it is like that way. 3 loop are there. Okay, now we get that carry equation. So for this equation, if we go for the further simplification, if you can, if you do, if you not can, you can implement by seeing this equation like that way. See, we need a x bar a bar b. Am I right, na? So see, here we give x a b and x bar a bar b bar. So there is a fourth term, 1, 2, 3, and 4. Fourth term, and all are added. That means, and this fourth individual term with relation with individual variable is AND. So that is why we need a 4 AND gate. That is why we implement 4 and 1, 2, 3, 4, and the all output are ANDed by a AND gate. So finally we get the S. And what are the relation it maintain? The first one get x bar a bar b. See, we give x bar a bar and b. The second one get x bar a b bar. So second one get, second one what, x bar. So it can get the input from C, X bar, then A, C from A, and B bar, C, the B bar. In that way, we can connect the individual every gate, then we can get the answer of S. And in same way, we can design the circuit of carry. So finally, we get the full adder circuit. Is it clear?
Sir,
Tell.
how you got the right one? How you got the right circuit from the left?
Right circuit from the left means? Tell me again.
No, the one on the right. The XA like. So this is the final one, the one on the right.
No, this circuit is for carry portion, and
carry,
this.
Oh, just the carry.
And this circuit is for some portion.
Okay,
See,
sir.
okay, this two individual circuit is needed to complete the full adder.
Oh, okay. So I thought it's two separate ones.
Two separate one. Okay. Now see, we can another process. We can easily make the full adder circuit by adding a two half adder circuit. We can show you here. See, by using a two half adder, if there is a provision to add a carry or get a extra input, then by using a two half adder we can create a full adder. So see here, it is a half adder circuit and it is again a half adder circuit. Am I right? These two one. See here, which we design. It is a half adder circuit. Am I right now? So check here. It is half adder 1, H1, and this is H2. But we need to add another circuit, another input, which is a carry. I told you na, your full adder circuit should have provision to add through 3 bit. Okay, so the third bit is implemented with a AND gate here, and finally we get carry. So by combine two half adder, we can get a full adder also. Okay, today may some extra pressure in your brain. I think I understand. So go with the study note. We will discuss in next class. Okay, first you read.
Sir, can I get the video, because there was a.
Obviously. Why not?
Sometimes, can.
Obviously. I will send the